Our final speaker will be Sebastián Løvengreen, who is a power system engineer that got his degree and master's in electrical engineering from the University of Chile in 2012. The next 5 years, he worked as a research associate and project manager at the Energy Center of the University of Chile. And in January 2017, he started his PhD at the University of Melbourne, Australia, under the supervision of Pierluigi Mancarella. His research interests include power system operation and expansion modeling, convex optimization, distributed and parallel computing, and energy policy and electric markets. Yeah.
All right, can you hear me?
Yes.
Okay, cool. I'll share my screen now. There you go. Can you see my screen?
Yes.
Beautiful. All right. So thanks for staying online, guys. I know that for most of you it's already late. For us here, the brave ones that got up early in this time zone in Australia, thank you for connecting as well. So the title of my presentation is Separation Event Constrained Optimal Power Flow to Enhance Resilience in Low Inertia Power Systems. We wrote this work along with Mehdi, Ghazavi, Dozein, and Pierluigi Mancarella. We are with the University of Melbourne, and also with Stephen Lowe, who is with Caltech in the USA. To provide some context to this work, you might be aware that, Australia has been experiencing loss of interconnection in recent years due to large events around the system. The first big one happened in 2016 in September, and a series of cascading events led to basically the disconnection of South Australia and the complete blackout of South Australia for several hours. It was a major issue here in Australia. And then in 2018, a lightning strike in the northern eastern side of the country tripped the interconnector between Queensland and New South Wales at a time where Queensland was transferring power from Queensland to New South Wales. So basically Queensland saw an equivalent load contingency and the rest of the system an equivalent generation contingency. And that led to high frequency events and low frequency events in corresponding areas. And then the problem continued to the point where South Australia became disconnected from the rest of the system, and also the frequency went up there, and it was a big mess, load shedding happening everywhere. No one went to complete blackout, but there was, we could say that some brownouts around the system. So in order to address this topic, we've been studying all the research in recent years about the modeling of frequency response constraints in OPF and unit commitment, in general scheduling problems. This research started a couple of 15 years ago, when they started sort of modeling frequency response constraints without the consideration of the natural response of demand. Then this evolved into the consideration of the natural response of demand in the last 5 years. And currently the research in this area is basically aiming to include fast frequency response and multi-service valuation of frequency response through the creation of closed expressions to relate all the relevant variables in this problem. So we basically, what we're doing here is we are using this frequency response model that considers the natural response of demand. We didn't include fast frequency response, although it's somehow easy to extend this work to fast frequency response the moment you have the model for fast frequency response. But the main idea is to basically focus on co-optimizing pre-contingency control variables and post-contingency response resources in order to limit the costs of the system that faces risk of splitting, actually. And what we do is we propose a model on OPF that allocates inertia and PFR resources in areas around the system to face both high and low frequency events in the system. This is interesting because in general, I mean, this research has always focused in low frequency events, and we're making an effort due to the fact that system splitting always leads to high frequency events in one of the areas that is getting sort of affected by the splitting of the system. So to start with sort of a recap of the modeling of frequency response constraints, in general, all the models are centered in this sort of single bus model of the system that consider that the system is just a single copper plate sort of model. And the idea is to take this single mass model and derive expressions for the different metrics that describe a frequency event. So here we have the rate of change of frequency, the quasi-steady state frequency, and the frequency in a year. And through this model, by evaluating this equation in different time periods, it's possible to derive these expressions for different metrics. And then by manipulating these expressions and using the targets for each of those metrics as in the reliability sort of metrics in a power system, it's possible to derive what we have called the frequency response security map, which basically depicts the security area considering all these possible metrics and that we've derived here from this expression. So we have tried to extend this concept to a multi-bus system, and we started playing with the maths, and we used equations to sort of mold that each of the buses in the system was representing a single mass model, and we were able to derive sort of considering that the contingency in this case is the loss of an interconnector and the complete splitting of the system into areas, we're able to derive expressions for the rate of change of frequency and the quasi-steady state frequency. The nadir and zenith expressions are not clear yet for us. I mean, we're working on that, and we assume in this work that basically we can use the single mass model for each of the areas to actually impose the nadir constraint. And so what we did is we created this OPF. I'm not presenting equations because in general it's very confusing. So the main ideas is we have the objective function which considers generation costs and loss load costs. Then we have the basic constraints of an OPF with the classic power balances and DC power flow in this case, transmission capacity, generator ratings, minimum stable generation. And then we impose a set of constraints that basically look to actually constrain the system frequency, considering that the system remains intact. So we are just taking the largest load contingency and generation contingency in the system as a whole, and we impose all the frequency that I showed from the recap for the single bus model. And that includes PFR requirements, frequency constraints, and system inertia as a whole. And also we are including the area frequency security, basically for those areas that can be formed when losing one particular interconnector in the system, we're able to impose corresponding constraints for PFR requirements by area, frequency constraints by area, optimization of flows between the areas, and high and low frequency events constraints basically for each of the corresponding areas. So these are part of the numerical results that we present in the paper. So if you consider that first we try these constraints without considering the area allocation of resources. So we're only focusing here on system-wide allocation of frequency resources. We see that if we focus on the interconnector between Queensland and New South Wales, here you can see a map. So we're looking at the transfer between Queensland and New South Wales, and the rest of the system is considered as a single area. All right, so if we impose the system constraints for the largest load and largest generation loss, we see that the system allocates upward PFR to basically constrain the largest loss of generation in the system, which is around 700 megawatts. And at the same time, it allocates a very small amount of downward PFR to limit the largest load loss, which is much smaller, like 400 megawatts. And of course, the natural response coming from demand, I mean, helps a lot here. So you see that the amount of PFR that needs to be allocated is basically responding to quasi-steady state frequency requirements. In that condition, the transfer between Queensland and New South Wales is over 700 megawatts. And we see that it's interesting because if we consider that this interconnector has some degree of likelihood of becoming sort of tripped during the next sort of time periods of operation, and we consider the economic allocation of reserves around the system, we see that since Queensland can eventually see this loss of transfer as a load event, basically as a loss of load event, we would need to have, downward PFR allocated to actually comply with the security requirements in Queensland when it becomes isolated. So, and due to the economic allocation, due to the fact that we're not really imposing the area constraints yet, we see that there is no allocation at all of downward PFR in Queensland. So one can expect if this interconnector gets stripped, things will go crazy in Queensland in terms of frequency. So yeah, that's the story. So what happens now with the dispatch of the system in case we impose these area constraints? We see immediately that the system responds in reducing the size of the potential contingency we can see between these areas. And as a matter of fact, the downward PFR allocated in Queensland to actually respond to the high frequency event that can happen goes up massively. And this is because the zenith constraint is becoming active because of the amount of inertia that we have in this area and the size of the corresponding contingency. But still the system is capable to find an amount of PFR to actually keep the system constrained. So, and of course, we run this for different high and low demand conditions, and you can see the results in detail in the paper. One other exercise that we did was to actually contrast these results with a dynamic model of the system. And this is what I show now. So basically what you can see here is what would happen if you consider the base case. So when the system is not being, the resources are not being allocated considering the area constraints. So if we assume that Queensland is triggered in that condition, the steady state constraint that would become active is the quasi-steady state frequency constraint. And we see that the dynamic model actually, if we simulate that contingency under those conditions, shows that actually the quasi-steady state frequency is exactly or very close to that of the steady state constraints. Then if we do the area allocation, we see that the zenith constraints becomes binding. And of course, there are many considerations regarding all these approximations, linear approximations necessary to actually approximate this very nonlinear, non-convex surface that is the zenith constraint, basically the original zenith expression. And although we're aiming to constrain for a zenith of 51 Hertz, the approximation at that operation point basically yields an actual target of 50.67 Hertz. And the dynamic model at the time, considering the allocation of resources, if we simulate the contingency in those conditions, we see that basically the result is robust and things are working okay. And the same way you can actually check what happens in mainland frequency, that is in the other areas that become disconnected from Queensland. And everything is in order. The same for the high load condition. If you compare the results from the dynamic model and the steady state constraints, things are in general very similar and in general robust, which is what is very important in this case. So just to wrap up, so low inertia power systems will require novel operational approaches to actually constrain the operation and operate the system securely. In particular, weakly mesh networks need to address this risk of separation in a sort of consistent way. And this is the purpose of the model that we're presenting in the paper. And we've shown in the paper that actually using this OPF to optimize the allocation of resources proves effective in preserving frequency stability after system split. And the dynamic tests, of course, show that this simple model through, a series of single mass models actually is a sort of effective way to achieve a secure operation of the system. And it's simple enough that can be applied in a linear way to different scheduling models that might be necessary to run the system. So that's my presentation, and I'm happy to answer your questions if you have any.
Thank you very much, Sebastián. You have a couple questions. I'm going to start with the one in the Q&A section because it's just a clarification. The question was on, I believe, slide 6, where you were showing the dynamic simulation results. What is the accuracy level for the model? Is it at milliseconds, seconds, minutes? The reason is I can't see excitation governor response models or other controller diagrams there. And this is from Terrence Mack, Georgia Tech.
All right. So yeah, I skipped some things, of course, for the sake of being concise and fit the presentation to the time slot. So in the paper, we present the considerations for the dynamic model. I have to be completely honest. I'm not into dynamics, so my knowledge and understanding of the precise model is limited. But I know that my colleague Mehdi, he ran all these simulations. We of course worked with a simplified model. We did some simplifications in regard to the parameters and the time, sort of the relevant aspects that we want to highlight here as dynamics, basically. So please refer to the paper to actually check the specific tuning of parameters and considerations for the dynamic model. It's a simplified dynamic model that basically is enough to prove to ourselves that using this simplified dynamic model is single mass model is sort of a good way to do the allocation of resources. I'm sorry if I'm a bit vague in my response, but to be honest, I don't want to lie regarding parameters and considerations of the dynamic model. So you can check that in the paper.
I think that's a very acceptable answer.
Yeah.
The other question is from Jose Daniel Lara, the previous speaker from UC Berkeley. He asked, how would you integrate other resources like fast frequency response reserves or other products to handle large frequency deviations? He also remarks that I would think that not including these fast frequency response reserves leads to more conservative results.
Yeah, absolutely. That's a very good point. The inclusion, the process to actually derive these constraints is, in general, there are two approaches. You can try to find sort of close expressions coming from this single mass model and deriving different conditions and finding the expressions and imposing them as constraints. And of course that can be done, and it's been done. There are two very good papers last year about using enhanced frequency response or fast frequency response and to allocate everything. What we've been doing here is actually we've been sampling sort of a set of points of operation, and then we've been calculating the convex hull for those points, and then we've displaced that convex hull to the point where actually the corresponding nadir or zenith constraint becomes robust. And so it's not impossible to, it's relatively straightforward to actually sample for different levels of fast frequency response as well and create sort of hyperplane that includes that effect as well. The results are conservative, but our focus was not to actually show the effects of fast frequency response. The target of this paper was to actually investigate the possibility to do a multi sort of variable allocation of resources in a system that faces splitting. And as said, I mean, we already have done the fast frequency response modeling, but of course it's happened after the presentation of this paper. So I agree with you. I mean, effectively the allocation is somehow conservative, but it shows that the purpose of the paper, I mean, it's achieved, in my opinion. Yeah.
Great, thank you very much. I'm not seeing any more questions, and we're over time by a couple minutes, so I think it's a good time to close up this session. I want to thank everyone for attending. I know these conditions for a conference are less than ideal, but I think we had some great participation today, wonderful talks, and so I appreciate everyone putting the extra effort to make this happen.
Thank you.
Yep, thank you very much.